Hello, I am Peyton Owen, and this is Lab 1, Constant Velocity for Physics 1. And today I'm going to talk about constant velocity. We simulated it in GlowScript using some code, and we also took some real-life data using the tracker app, so let's get into it. So what even is constant velocity? Constant velocity is an idea in physics that basically means that an object is moving in usually a straight line at a constant speed, and it has no net forces acting on it. Since it's moving at a constant speed, it's not accelerating, it's not decelerating. So net force is zero, it's moving constantly. So the purpose, what even is the purpose of this lab? The purpose of this lab is to learn more about constant velocity, obviously. And as I mentioned, we took coded data and we also took real life data, so we're going to compare what they are. Is the computer simulated constant velocity better, or is real life data better? And here are the results, just quick and easy. While the data is similar for both, it actually shows that the GlowScript data, this one, went farther in roughly the same amount of time, and this is due to the lack of friction simulated. We'll talk a lot about friction being the main difference between these two. So you can kind of see it starts to curve off and slow down a little less steep. Well, here it's straight, and that's going to be due to friction. This is true constant. This is constant in real life where friction is involved. And here's the experiment. I'm going to show you the video. So nothing crazy special. We just kind of rolled a marker.
Sure.
So in this, the system was the marker and the surrounding was the table. The initial conditions for the data we took was that the marker was rolling. As you can see, we kind of started right about here, or not here, right about here. So it was already rolling, and then we stopped here and took our data. So we set up a simple experiment where I just showed you we rolled the marker, and then in the tracker app you can put dots on it, and it'll track those dots, and it'll show you the distance it moves using this meter as a guide stick. And by having that distance, tracking computed the velocity of the marker. It's really just a simple way to kind of model constant velocity. So what were the physics behind this? So I talked about net force. Since we're dealing with constant velocity, you can safely assume that net force is zero. No acceleration, no deceleration. We are looking at the forces after it's been pushed, so the net force from pushing on it is zero. Objects are only at equilibrium, so net force equals zero, when they are either at rest or at constant velocity. Those are the only two times you're going to get that. So in this video, you can see, we'll just talk about the principles implemented. In the video, you can see that one of my lab partners pushed the mark across the table, released it, and let it roll. Right after they release it, it stays at a constant velocity for a short time until friction obviously slows it down. Once again, friction showing up. So here are the equations. Net force F net is equal to mass times velocity divided by delta t, or change in time. Velocity update, final velocity equals initial velocity plus F net over m times delta t. Position update, final position is equal to initial position plus initial velocity times change in time, plus 1/2 times F net delta m times time squared. Since we are at constant velocity, F net is 0, and the initial velocity will equal the final velocity. Self-explanatory. So let's just talk about the tracker. And I can show you here that this is the tracker video. Those are the dots I was talking about. It's kind of hard to see. Can I pull up full screen? These are dots that show, and I'm going to replay back here. You can see this moving up and down. That's the different dots. So that exact graph that I showed you earlier in the slides is that exact graph right there. So it taking the dots and the time that the dots are at and spreading them out over that distance gives you the real life constant velocity. Now let's talk about GlowScript. So this is just kind of the code I used. This is the important codes. So this is the ball position vector, that's where it was. This is the ball velocity vector, that's how fast it's moving. While time is less than 3, because it's only 3 seconds. And here's the vector update, since it's at constant velocity. It's not really doing too much. And then here is the simulations compared. for GlowScript. This is the picture it gave me. This is the graph. The analysis. This is them. I showed you earlier. And this is them overlaid. This is the GlowScript one. Obviously, straighter, longer, and faster. And this one is constant velocity. Probably just a little bit slower. So the graph looks different, and that is to be expected. Computer simulations can ignore things that we can't in real life, like friction. However, both graphs show that a constant velocity and a possible error would be friction. In conclusion, constant velocity is a whole lot easier to simulate, and that's just true. Real life constant velocity can be brief, as we saw, so it'd be easier to see on computer simulations, but real life data will always be a little less constant than simulated data when ignoring friction. And that's it.